All right, let's talk about chemical equations. All right, so in this little video, we're going to talk about chemical equations and how to understand them on the macroscopic level, the microscopic level, and the symbolic level. Remember, in one of our earlier lectures, we talked about these. Talked about these as three different representations, right? And those are three different ways to describe or think about any kind of a chemical process. And the real goal of chemistry, understanding chemistry, is to kind of understand all of these three together, right? So we're going to be looking at that. We're also going to look at properties of the elements, their standard states, including diatomic elements. We'll talk about balancing chemical equations and states in chemical equations. All right, so here's a simple chemical reaction. Sodium reacts with chlorine to make sodium chloride. And that simple description might call to mind a macroscopic representation where we think of what this reaction actually looks like. And so if we've got this flask here and it's full of chlorine gas, you can see that kind of yellowish greenish gas in that flask. That's chlorine, and you can't really see it, but there's a little tiny piece of sodium down here. And if you heat that up or find some other way to initiate that reaction, once it gets going, it's a really vigorous, even violent reaction. The sodium reacts with the chlorine. You get a lot of heat and light coming off. And I couldn't find a picture of it to include over here. But when you're done, you end up with a flask like this. And the sodium chloride that's produced is produced so hot that instead of looking like a crystal, it comes off as sort of like a powder, and you just end up with this white powder coating the insides of the flask at the end of that reaction. All right, so this is a macroscopic representation of what this process looks like. Sodium reacts with chlorine to make sodium chloride. All right. We can also think about the microscopic representation. And the microscopic representation of this reaction would look something like this. We've got a bunch of sodium atoms here, and we've got a bunch of chlorine molecules. We'll talk a little bit more about diatomic species in a little bit. I think we've mentioned this before, but chlorine is one of those that always exists in pairs. So we've got chlorine molecules, and they react to make sodium chloride. This is our product over here, and this product, this is an ionic compound, so it's not shown here in the diagram, but each one of these sodiums becomes a sodium ion. Oh, let's use red here. So each one of these sodiums is now a sodium ion with a positive charge, and each of these chlorines becomes a chloride cation with a negative charge. And so this is what our product looks like. Now we can also look at a symbolic representation, right? Both the macroscopic and the microscopic are useful. They're good descriptions, but it's hard to write that, right? We don't want to have to draw these pictures every time. So the symbolic representation is a way to do this much more concisely. And so for our symbolic representation, what we want to do is write the reacting species over here, sodium, and this is reacting with chlorine. And when these react, they produce sodium chloride. Okay. All right, these guys on the left, the sodium and the chlorine, things that are reacting, these are called the reactants in the chemical reaction. And the things that are being produced, in this case it's just one, but it could be multiple things. The things that are produced are called the products of the chemical reaction. So we write our chemical equations with the reactants on the left, the products on the right, and this arrow in the middle means basically that the reactants are being converted into the products. Now, if you've done these chemical equations before, you can see there are some things missing here. This equation isn't balanced, and we don't have our states in. We're going to come back to that and fix those things in just a minute. Okay. But first, I wanted to just mention that, as I said before, the point of chemistry, right, the point of talking about these chemical reactions, chemical equations, is that we want to get to a point that when you see a chemical equation, it calls to mind both the macroscopic representation and the microscopic representation. And in fact, this equation, in a sense, means both of these two things simultaneously. And so if you're working with chemical equations, if you're just thinking about this, then you're doing it wrong. Right? There are a lot of important things we can do with the symbolic representation, but remember that the symbolic representation means both this and this. And so those are the things that we ultimately really should be thinking about. All right. Now, in writing our equations, we need to also include the states of the species involved. And if we have something new like, hexanol or something, usually you'd be told hexanol is a liquid, right? Or if we've got nitrogen trichloride, you'd be told nitrogen trichloride is a gas or whatever. But there are some things for which you should know the states, and the elements are one of those things. Okay? And for the elements, the states of the elements are pretty simple. There are a bunch of gases, and the gases fall into two groups, basically. One is the noble gases, which is just this column, this rightmost column. I'm going to go down to radon. I'm not going to. You could include that if you want, but that's a recently discovered radioactive substance. It's not something that you can really study in the macroscopic sense. It's something that exists and then decomposes in a fraction of a second. So as far as species that we can really study and talk about, the noble gases are these guys over on the far right: helium, neon, argon, krypton, xenon, and radon. Right? And then the other gases are things that you are either very familiar with or somewhat familiar with that you should recognize as gases. Right? And those include hydrogen, oxygen, and nitrogen, which you should be pretty familiar with. Fluorine, which might be new to you. And chlorine, right? So it's the noble gases, and then these guys here. All right. So those are gases, you should know that. And then there are liquids. These are easy because there are only two liquids. One, you probably know, mercury here is a liquid metal. And then bromine, which again is probably new to most of you. It's kind of an orange liquid stinks like crazy. Right? And when we talk about standard states, what we mean is this is the state that these would be in under normal conditions, room temperature and one atmospheric pressure. If you make them very cold, of course, you could freeze mercury into a solid. You could freeze bromine into a solid. But under normal conditions, the standard states, mercury and bromine are liquids. So there are just two of those. And then solids, obviously. Solids are just everything else. Okay. So when you're writing or discussing chemical reactions, you should be able to recognize the states of most species. For all of the elements, you should know this. Know the gases are the noble gases plus these few that you're familiar with. There are two liquids, mercury and bromine, and everything else is a solid. Okay. For compounds, let me put these here. For compounds, if it's something that you're very familiar with, like water, right? We might not mention that water is a liquid and expect you to know that water is a liquid when you're balancing equations. Right? Although, of course, sometimes water can be produced as steam if the reaction gives off a lot of energy. Right? But one thing that you should know, I think we mentioned this before, when we're talking about the properties of ionic compounds and molecular compounds. Ionic compounds in their standard state are always solids. Ionic compounds have melting points of several hundred degrees Celsius. So anytime you see an ionic compound like sodium chloride or lithium sulfate or potassium nitrate or iron hydroxide, any of those things, you can assume that that substance is a solid. If you have a molecular substance like carbon tetrachloride or nitrogen dioxide or methanol or something like that, then typically the problem will tell you whether that substance is a solid, liquid, or a gas. But for ionic compounds and for all of the elements, you should be able to predict whether something is a solid, liquid, or gas just based on the knowledge that you have. All right. We also need to talk about diatomic elements. As we said before, there are some elements that just always exist in pairs. You can think about them this way, with a bond between them, or you can think about them just as two atoms kind of stuck together to make a diatomic molecule. And there are a few elements, there are 7 of them, that always exist, or at least under standard state conditions, always exist as diatomic. And so let's look at those. These, fortunately, are really easy. I remember my Gen Chem professor told me a trick about these diatomic elements that I've remembered ever since. And it's all based on the number 7. And so to remember what the diatomic elements are, you start with nitrogen, which is atomic number 7, and then you make the shape of a 7, right? So you get nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and that's only 6, right? N2, O2, F2. And then if there's going to be a troublemaker, if there's somebody who doesn't behave as you would expect based on its position in the periodic table, what do you think that's going to be? Right? As always, that's hydrogen. Right? So I'll add hydrogen just to make it tricky. Right. So these elements, anytime you see them as elements in a chemical equation, unless there's something very unusual happening that's described in the problem, you can always assume, and should always assume, that these are diatomic molecules. Existing like that. Okay. All right. So let's go back to our equation we had before. A couple things we need to do is we need to balance this equation, and we balance equations by putting in what are called stoichiometric coefficients. These are numbers that we insert before the substance. There are two different kinds of numbers in a chemical equation. Right? There are subscripts, right? And the subscripts tell you how many of each atom are in the molecule. So these basically describe what the molecules look like. So that Cl2 means that this chlorine exists in little bundles of 2, right? That the chlorine is diatomic. The other number are the stoichiometric coefficients. Okay. And this comes from more stoichiometry, and stoichiometry means the amount or counting the atoms, right? It ultimately comes from Plato, who used the word stoichio or stoichion or something like that. I don't remember exactly what it was. Is the word for seed, and he used that in a chemical sense, and that term has stuck. And so now whenever we talk about stoichiometry or stoichiometric, what we're talking about is balancing the number of atoms in a particular chemical process. All right. So this has to be balanced so that we have the same number of atoms on the product side as we have on the reactant side, because when a reaction happens, we can't create new atoms, right? The number of atoms that we start with has to be the same as the number of atoms that we end with. So if we want to balance this, there are there's one quick and easy way that we can do this, and I want to put this up here, although this is wrong, right? We've got 1 sodium on the left, 2 chlorines on the left, and on the right we've got 1 sodium and 2 chlorines. Right? So we could balance this by putting a 2 here, right? But we can't do that because whenever you change one of these subscripts, you're changing the identity of the substance itself, right? Where NaCl means means that you've got a substance that looks like this, and of course it's ionic, so we've got charges. If you put a 2 there, then you're changing it to this substance, right? You've made a new chemical species, right? And we can't do that, right? We absolutely can't do that because we need to keep the species as they are. Right? We don't want to change the identity of the things that are reacting. So the only way to balance this then is to change the stoichiometric coefficients, right? And so if we look at this one, if we've got 2 chlorines on the left, we have to have 2 chlorines on the right. And since we can't change this number down here, we'll put a 2 here. So now I've got 2 chlorines on the left and the right, but now we have 1 sodium on the left and 2 sodiums on the right. So we'll put a 2 here, and now we have a balanced equation. Right? 2 sodiums reacting with 1 diatomic chlorine molecule, giving us 2 sodium chlorides. Okay. And anytime you leave the stoichiometric coefficient out, it's assumed that there's a 1 there. I guess you could write the 1, but people generally don't. And it would look really weird and kind of clumsy if you did that. So if you just leave that space blank, then that's assumed to be a 1. And so this is how we would correctly balance this problem. All right. The other thing that we need to do is include chemical states. Right? To have a complete description of the process, we need to include the states of the species that are reacting. And so if we go back to what we talked about before, sodium is an element, and we said there are, a handful of elements that are gases, there are 2 that are liquids, and everything else in their standard state is a solid. So sodium is a solid, right? Chlorine is one of those species that's a gas. So we want to include that sodium chloride is a gas, or excuse me, that chlorine is a gas, and sodium chloride is an ionic compound, and all ionic compounds are solids. So that's how we would write this this equation. Now that we've got it balanced and we've included states, now this equation is finally correct. All right, and just as a reminder, when you're including states in chemical equations, we got a couple of options. We've got solids, liquid, gas, and then one other one, aqueous, which we write as AQ, and aqueous means dissolved in water. So when we're talking about solutions, something that's in solution, we want to append AQ in parentheses after that species. All right, so when we're writing equations, here are the things we need to do. One is start by putting the reactants, that's the reacting species, on the left. We have an arrow, and then on the right, we write the products. Okay. Use what we've learned about chemical nomenclature to write the formulas correctly. And this is really important because the subscripts on there indicate what the chemical species is, and if you change the subscript, you're changing the species. So in order to describe it properly, you've got to get these subscripts correct. And then once you get the subscripts correct, don't ever change them. When you go to balancing, don't change them, because then you would be changing the actual species involved. Okay. All right. Then once you've got the species listed correctly, include the states of everything, remembering what we learned about the different elements, and that ionic substances are always solids unless the reaction is taking place at a very high temperature. Right? And then finally, balance the equation only by changing the stoichiometric coefficients, that's the numbers before the chemical species, to make sure they have the same number of atoms of each element on both sides of the equation. All right. Okay, let's practice a couple of these, couple of simple ones. Okay. So let's take this reaction. Nitrogen monoxide gas reacts with oxygen to form gaseous nitrogen dioxide. Okay. So you notice we've got nitrogen monoxide gas, and since nitrogen monoxide is not something that you would necessarily know what the state is, it's provided in the equation here. So got nitrogen monoxide, that means one of each atom, and it's a gas. It reacts with oxygen. Now oxygen, nothing else has been provided here because oxygen is an element, and so we should know that oxygen is both diatomic and in its standard state is a gas, and this forms nitrogen dioxide in the gas phase, right? And we'll use what we remembered about nomenclature. Nitrogen dioxide is NO2, and the problem tells us that it's a gas. All right. So we've got all of our species written correctly. We've got our reactants on the left, our product on the right. We've included states, and now we just need to balance it. And we've got two oxygens on the left and 2 oxygens here. That's fine. Oops, no, we got another oxygen here, so we've got 3 on the left and only 2 on the right. So if we look over here, no matter what number we put in this here for the stoichiometric coefficient, 1, 2, 3, 4, 5, whatever, we're always going to have an even number of oxygens. We're either going to have 2, 4, 6, 8, 10, so on and so forth. So we need to get an even number of oxygens on the left-hand side. We could do that if we put a 2 here. This would give us 2 nitrogen monoxides reacting with 1 oxygen to give us 1 NO2. Okay. That's good. We've got even number of oxygens on both sides, but now we've got 2 nitrogens on the left and only 1 on the right, 4 oxygens on the left and 2 on the right. So we could fix this by putting a 2 here. Now we've got 2 nitrogens on both sides and 4 oxygens on both sides. All of our chemical formulas are written correctly, and we've included all of our states. So that one's good. All right. Hydrogen and oxygen react to form liquid water. Now, water, water can exist as a gas, but in this case, they're specifically telling us it's a liquid. And if you didn't know, I would assume that it's a liquid because that's what it's going to be at room temperature. So for hydrogen and oxygen, those are both elements. We have to go back to what we remember about the elements. So hydrogen, we know, is a diatomic gas. Oxygen is also a diatomic gas. And water, they told us, was a liquid. We've got the same problem here as we did last time. No matter what we do here with our oxygens, we're going to have an even number of oxygens on the left-hand side. So we need to get an even number of oxygens on the right. So we can do that by putting a 2 here. And that almost gets us where we want, except that we've got 4 hydrogens on the left and only 2 on the right. So we can fix that by putting a 2 here. Okay. All right. So this one is complete. And you might think also about, when you're doing these, you might think about, let's use white. White's more commonly used for hydrogen. So you might think about this in terms of a microscopic representation at the same time, right? But this is what we're focusing on now. All right, one more practice problem. All right, this one's a little bit trickier, but why don't you take a crack at this one? Hit the pause button, read this statement, hit the pause button, try to write this as a chemical reaction, and then unpause it and we'll compare our results. All right, so magnesium, right, placed in a solution of hydrochloric acid. So we're reacting the magnesium and the hydrochloric acid. So those are going to be our reactants. Right? And solution of hydrochloric acid, remember what we talked about with in our nomenclature section. Hydrochloric acid is HCl, and says that it's a solution, so we can put AQ there. Also, you remember if hydrogen, if HCl is in the gas phase, we call it hydrogen chloride instead of hydrochloric acid. And then the products are dissolved magnesium chloride. Here's our magnesium chloride. All right. And then you need to go back and think about what we learned in ionic nomenclature. Remember that magnesium is a +2 ion and chloride is a -1 ion. So the correct formula for magnesium chloride is MgCl2. Okay. And then the other product is hydrogen gas. Which we know is a diatomic gas, right? Let's come back to our magnesium because we didn't finish that part. When placed in a solution of hydrochloric acid, magnesium reacts magnesium. Remember, we've got a handful of gases, 2 liquids, and everything else is a solid. So magnesium, under standard state conditions, would be a solid. All right, and now we're almost done. We've got everything written correctly. We've got all of our states. We just have to balance things. And everything is almost balanced, except we've got 2 chlorines here and only 1 chlorine here. So we can fix that by putting a 2 here. And that simultaneously fixed this problem over here because we also have 2 hydrogens. Putting a 2 in front of the HCl gives us 2 hydrogens to balance with the H2 on the product side. All right, so that's it. And that one is now correct and balanced. All right, so what did we do in this one? We looked at ways to understand chemical equations in terms of a macroscopic representation, just a statement or a description of something that we would actually see. We talked about the microscopic representation, thinking about the atoms and the form of all of the chemical species on the left and the right. And then we took that and we're learning about how to rewrite that in a symbolic representation. And that symbolic representation is that chemical equation. In order to do that, we had to review a little bit on the properties of elements, remembering which ones were solids, liquids, and gases, and the 7 elements which are diatomic under standard conditions. Those 7 start with element number 7, which is nitrogen, make the shape of a 7, and then, because that only gives us 6 of them, also add hydrogen to that. That gives you the 7 diatomics. Once you've got a chemical reaction that is written correctly, you need to balance it, and balance it only by changing those stoichiometric coefficients. If you change the subscripts, you're changing the identity of the species in the reaction. So balance only by changing the stoichiometric coefficients. And then we also talked about adding states. And there are 4 common states that we use: solid, liquid, gas, and aqueous for dissolved species. All right, terrific. That gets us through chemical equations, and we'll be back with something else in a little bit.